Hello everyone, in this video I want to talk about how to solve absolute value inequalities. But before we talk about how to solve absolute value inequalities, I want to do a little bit of a review of the absolute value function and make sure we understand this really important interpretation that can help us solve actually lots of problems involving the absolute value function. So there's several different ways to interpret or work with the absolute value function. So here we're considering the absolute value of some number x, and a really informal way to think of the absolute value function that works when it comes to evaluating the absolute value function is, well, the absolute value function just makes x positive. So if x is already positive, it doesn't do anything, and if x is negative, well, then it just makes it positive. We can also define the absolute value function as a piecewise function, which does exactly as I just said. If x is less than 0 or negative, we take our negative x value and multiply it by -1, but all that does is make x positive. And if x is greater than or equal to 0, x just remains x, nothing happens to it, and it still is positive. The other interpretation for the absolute value function that is going to be really important for us here, and especially in classes like calculus, is the absolute value function is really describing how far a number is from 0. So when we look at the absolute value of x, that is telling us how far x is from 0. Right? If we think about a number line, and maybe 0 is right here, and then we think about, like, maybe say the absolute value of 3 and the absolute value of -3. Well, what we know is that the absolute value of either of these numbers is going to be +3, and we can take that back to our distance interpretation. The absolute value of 3 or -3 are both 3 because the distance -3 or 3r from 0 is 3 units. So it's pretty straightforward how the absolute value function works when we have a single number inside of our absolute value brackets. It just makes that number positive or tells us the distance that number is from 0. But we're going to run into quite often are expressions where we have x minus some number inside of our absolute value brackets or x plus some number inside of our absolute value brackets. And we want to make sure we know how to interpret that from the distance perspective as well. And so to help us do that, I want us to consider a couple little examples. Let's go ahead and first look at the difference between -2 and 3, and then we'll look at the reverse difference, the difference between 3 and -2. And the reason why I want us to consider the difference or the subtraction between these two values is because the process of subtraction can also be related to distance in a way similar to how the absolute value function is related to or can be interpreted in terms of distance. Right? If we take the difference between two numbers, what we're really learning about those two numbers through that difference is the distance between them on our number line. For instance, if we look at the difference between -2 and 3, that's -2 minus 3, we know that that is equal to -5. And so the idea here is -2 minus 3 is equal to -5. We can interpret that from this distance perspective. The distance between -2 and 3 is -5. And all the negative sign is indicating is the direction we have to travel. So how far is -2 from the value of 3? We know it's 5 units apart. We have to travel 5 units to the left of 3 to end up at -2. So all that negative sign is indicating is the direction, but if we throw all this in absolute value, then we just care about the distance and not the direction. So now if we look at the absolute value between -2 and 3, that's going to be +5 because the distance from one of these numbers to the other is 5. If we look at the reverse difference, that should give us the same distance just described in a slightly different way. Right, 3 minus -2 is equal to +5, and that makes sense if we think about it from the distance perspective. The distance between 3 and -2 is 5 units. How far do we have to travel from -2 to get to 3? We have to travel 5 units from -2 to get to 3, and the direction we have to head in is the positive direction or to the right. And so again, the absolute value of 3 minus -2 is just the absolute value of 5, or 5 itself. And so if we want to interpret the absolute value of x minus a is equal to something from the distance perspective, all this is telling us is the distance between x and a is equal to whatever follows or whatever is on the other side of our equation, or eventually an inequality. And so again, the point of this little example off to the side here was to help us extend this interpretation of the absolute value function for when we have a difference inside of those absolute values, which is what we're going to encounter a lot more often than just an x inside of our absolute values. When we had just x inside of our absolute value, that quantity could be interpreted as describing how far x is from 0. That's like setting a equal to 0 over here. But now in a more general situation, if we have the absolute value of x minus a, we can interpret that as describing the distance between this first number x and the second number a. And you got to be careful when you're setting this up. We have to have that subtraction sign here. So if this looked like x plus a, we'd really have to think of that as like x minus a negative a. All right, so let's go ahead and apply our new interpretation of the absolute value function to help us solve an absolute value inequality. So here we're interested in solving the absolute value of the quantity x minus 1 is less than 3. And so we will eventually come up with an algebraic procedure to solve this very quickly. But let's take our time with this first example and first break it down into a verbal statement of how this inequality is describing the distance between some numbers. And so on the left-hand side of our inequality, we have the absolute value of a difference. So we have our setup over here. The absolute value of x minus a in general is describing the distance between x and a. Here our a value is 1. So the absolute value of x minus 1 is saying the distance between x and 1. And then the rest of the inequality is describing what we know about the distance between those two numbers. So let's go ahead and write this down or translate it into words. And so the absolute value of x minus 1 can be interpreted as telling us the distance between x and 1 is, and then the rest of our inequality says less than 3, and that's exactly what we know about the distance between x and 1. The distance between x and 1 has to be less than 3. Or another way of phrasing that is x is within 3 units of the value of 1. So maybe 1 is on our number line right here. Then we can go up to 3 units to the right, or up to 3 units to the left of 1, and still have all these potential values that we're calling x satisfy our inequality. So if we go 3 units to the right of 1, we'd be at 4. And if we go 3 units to the left of 1, we would be at negative 2. And so if we graph on our number line all these x values that are actually within 3 units of 1, we get this little interval from negative 2 to 4, and we do not include the endpoints of the interval. Right? Remember, the way we indicate the exclusion of those endpoints is we use an open circle at the endpoints. If we used a filled in or closed circle at the endpoints, that would indicate that they are included as part of our solution set. So there's usually a few different ways these solution sets are described. Using a number line, we can graph it like we've seen here. Another common way to describe our solution set to an inequality is using interval notation. So this would be the open interval from negative 2 to positive 4. Remember, for this interval notation, the parentheses are like our open circles. It means we do not include those endpoints. And if we had square brackets, that would be like having the filled in circles where we do include the endpoints. So we've seen this graphical way to describe our answer, this interval notation to describe our answer. The last way is using inequalities, or sometimes on top of inequalities, what we call set builder notation. But if we were describing this using a single inequality, it'd be all the x values between negative 2 and positive 4. Right? These are the numbers whose distance between these numbers and 1 is less than 3. And from our number line, we're going to reverse engineer how we could solve this algebraically. And the first thing I want us to focus on to help us figure this out are these endpoints. If we plug these x values of negative 2 and positive 4 into our original inequality, what would happen? Well, negative 2 minus 1 is negative 3, so that would correspond to like the absolute value of negative 3. That's equal to positive 3, not less than 3. That's why we exclude that endpoint, but it's as close as we can get to our solution set without actually being in it. And the same thing happens over here on the far right when x is equal to positive 4. 4 minus 1 is 3. The absolute value of 3 is equal to 3, not less than 3 again. That's why we exclude that endpoint, but it is still as close as we could get just on the other side. So what we can notice is on the far left, this x value really made our absolute value expression equal to negative 3, or that number on the other side of our inequality. And on the far right, that is when our absolute value expression obtained that value on the other side of our inequality. So on the far left, this expression obtained the value of negative 3. On the far right, this expression obtained, or really I should say almost obtained, the value of positive 3. But what was the expression algebraically that was actually getting close to these values? It was x minus 1. That was our expression. And so now if we look at the difference between x and 1, that's describing the distance between x and 1, well, that could be equal to 3. That would correspond to this point at 4 if the distance was actually equal to 3. But we want that distance to be less than 3. Similarly, if we look at what happens on the far left, here we'd have x minus 1, or the distance between x and 1, equal negative 3. Here that negative is just indicating direction. We still want to include all these x values that get us to x minus 1 is equal to 3, but also less than negative 3. Or I should say greater than negative 3. Because remember, if we're greater than something, then we're to the right of something. If we're less than something, then we're to the left of something. And so from our original absolute value inequality, our distance interpretation, and the graphical representation on our number line, we saw that an equivalent way to express our inequality is with this compound inequality that says negative 3 is less than the quantity x minus 1, which is less than positive 3. And to take this a little bit further, we can really isolate x in the middle of our inequality just by adding 1 to each side. Well, if we add 1 to the left-hand side, we get negative 2. If we add 1 to the middle, we're left with just x. And if we add 1 to the far right, well, then we end up with positive 4. And well, this is the inequality version of our solution set that we saw from interpreting the graphical or distance interpretation of our inequality. And so from this example, we can generalize how to solve basically any of these absolute value inequalities with the absolute value of some expression is less than a number. And so in general, if we encounter something like the absolute value of x minus a is less than some other number b, then the solution can always be found by solving the compound inequality negative b is less than x minus a is less than b. And these are definitely the most popular or most common types of absolute value inequalities that you should encounter. And so when it comes to manipulating inequalities, basically you can use the exact same set of rules that you use for manipulating or solving equations. The one thing we have to remember is that if we multiply or divide both sides of an inequality by a negative number, then we have to switch the direction of the inequality signs. Another thing to note is that this kind of general formula for solving an absolute value inequality with a less than inequality sign in general is this inequality sign is important. We do need a less than inequality, but we can also swap this out for a less than or equal inequality. And if we do that up here, then we have to use less than or equal inequalities down there as well. So now we're going to run through a very, very similar example to the one we just saw, except we're swapping out that less than sign with a greater than inequality sign. So now we're tasked with solving the absolute value of x minus 1 is greater than 3. And if we're going to go through the same motions that we did for our previous example, we're going to start with the distance interpretation. So we can read this as the absolute value of x minus 1 is greater than 3, tells us the distance between x and 1 is greater than 3. So now with that physical or distance description of our solution set, these x values, we can go ahead and describe the entire solution set to our inequalities. So we just have to kind of figure out graphically what are all the x values such that the distance between x and 1 is greater than 3. Or I think maybe a friendlier way to phrase that is equivalently, this is saying x is more than 3 units from 1. Well, which x values or numbers are exactly 3 units away from 1? Well, we can go 3 units to the right and end up at positive 4, or we can go 3 units to the left and end up at negative 2. We don't want to include the values in between negative 2 and positive 4 because those would be the x values whose distance between 1 is less than 3. We want the distance between these x values and 1 to be greater than 3. So we have to go more than 3 steps to the right or more than 3 steps to the left. And so that's really describing the opposite set of numbers that we saw in our previous inequality, or sometimes that's referred to as the complement. So when we solved our absolute value inequality with a less than or a less than or equal to sign, and we saw we had a solution set that was a single interval. In the other case where we're solving absolute value inequalities, where we have a greater than or equal to sign, we see that we're pretty much always going to get 2 intervals in our solution set. So now let's go ahead and describe these 2 intervals using some of our alternative notations. I believe we looked at interval notation first for the last example. So how we describe these 2 intervals using interval notation. Well, our first interval starts at negative 2 but doesn't include negative 2 and goes to the left forever, or we say to negative infinity. So here we have the open interval from negative infinity to negative 2. Right? We used curved brackets because we do not include either of these values. And then we have to join that with this other interval from 4 to the right, or from 4 to positive infinity. And so now this is a bit of set notation that we're not going to spend a whole lot of time going into because this is pretty much the only place we're going to use it. But if we want to say that we are joining these 2 intervals together, or think about like almost adding these 2 intervals together, we use this capital U sign, which stands for the union of those 2 intervals. So this notation is describing all the x values from negative infinity to negative 2, as well or in union with all the x values from 4 to positive infinity. Those are all the solutions to our original absolute value inequality. And so the third way we saw to describe our solution set was not graphically or using interval notation, but using inequalities or sometimes set builder notation. So if we want to describe this using inequalities, we could say it's all x values less than negative 2 or x values greater than positive 4. So those are 3 equivalent ways to describe the same solution set to the same inequality. A couple other notes about this third way to describe our solution set using more inequalities is we don't always have to write the full version of these inequalities that go to infinity. Right? Equivalently, we could write that x is less than negative 2 implies that x goes all the way to negative infinity. So these are equivalent. It is not necessary to write the negative infinity like it was for our interval notation. And similarly, we could have said that x is greater than 4 while being less than positive infinity. These are equivalent. You can't actually do it either way. This first one in pink is just a little bit more concise. So what we saw, and this again, we're just going to kind of reverse engineer our solutions, starting with this inequality version of our solutions. We had x is less than negative 2, or x is greater than 4. So this is saying all these x values that are to the left of negative 2 are part of our solution set. All these x values to the right of positive 4 are part of our solution set. Remember, our solution set was really coming from answering this question up here. Which x values have a distance more than 3 units from 1? So what we really want to do to get back to there is maybe have, instead of x showing up in these inequalities, that original expression x minus 1, because then it'll be describing the distance between x and 1. So if we want to have that -1 show up in our inequality to get us closer to our original form, let's go ahead and make it happen. But we're not just throwing a -1 in there without any consequence. We're treating this just like we would an equation. Whatever we do to one side, we have to also do to the other. So technically, we subtracted 1 from each side of this inequality, or from the left-hand side. So we have to also subtract 1 from the right-hand side. If we do that for our second inequality, then we run into something that we saw earlier, or similar to what we saw earlier. So now we have x minus 1 is less than -3, or x minus 1 is greater than +3. And we know that these together form the solution to the absolute value of x minus 1 is greater than 3. And so now that we've gotten back to how our inequality in question was originally stated, the absolute value of x minus 1 is greater than 3, we can kind of work backwards to see a general strategy for solving this type of absolute value inequality. And so in general, if we're trying to solve an absolute value inequality with a greater than inequality sign, or a greater than or equal to inequality sign, so say we have the absolute value of x minus a is greater than b, then we have to solve two separate inequalities individually, separated by the word or. And so we have to solve x minus a is greater than b. That's the same as up here where we solved x minus 1 is greater than 3. We just drop the absolute value signs and solve the inequality how it is. Or we have to solve x minus a is less than -b. And that corresponds to up here where we solved x minus 1 is less than -3. There are, of course, other ways to kind of derive this or think about it. Remember that one of the other ways we thought about the absolute value function initially was if the absolute value of our quantity is positive, it does nothing. That's what we see here. And if the thing inside of our absolute value is negative, we multiply everything by -1 to make it positive. That's pretty much what is happening over on this inequality, except remember, when you multiply both sides of an inequality by -1, it turns our b negative, but also reverses the sign or direction of our inequality. All right, everyone, I got one more example of an absolute value inequality that I'd like us to solve together because it looks a little bit different than those simple examples that we saw earlier, but we still solve it using the exact same processes. So here we are tasked with solving the absolute value of the quantity 8 minus 2x is less than or equal to 4. So the first thing we do is isolate our absolute value expression on one side of our inequality and everything else on the other side. And then we determine, do we have a less than or greater than type of inequality? Well, here we have our isolated absolute value sign, followed by a less than inequality. So we are in that less than or equal to case. And I think these are the easier cases to handle because when we have a less than or equal to type of absolute value inequality, we can solve it by translating it into a single compound inequality. So we drop the absolute value signs at a cost of making it a compound inequality. On the far left, we have our negative value, in this case -4, and on the far right, we just have the original far right-hand side of our inequality, +4. And so now remember, our goal to solving a compound inequality is to isolate our variable of x in the middle of our inequality. And we follow the same steps we do for solving an equation, with the extra rule that if we ever multiply or divide both sides by a negative number, we have to reverse the direction of our inequality while doing so. All right, so if we're going to solve this for x, the first thing we're going to want to do is get that 8 out of the way, get that 8 out of the middle, by subtracting 8 from all three sides of our inequality. Well, on the left-hand side, we have -4 minus 8 is -12. That'll be less than or equal to our new middle, which is just going to be -2x, which is going to be less than or equal to our new right-hand side. 4 minus 8 is -4. And so now we have one more step to go to finish solving our inequality, and that's dividing both sides by that factor in front of x, that -2. But we have to remember that special rule for working with inequalities. We've divided both sides, or all three sides of our inequality, by a negative. So now we're going to have to reverse the direction of our inequality signs. So our less than or equal to inequality signs have to reverse to become greater than or equal to inequality signs. All right, so now the rest is just simple arithmetic. Negative 12 divided by negative 2 is positive 6. Negative 2x divided by negative 2 is just x. And negative 4 divided by negative 2 is positive 2. And so now we have the solution in the inequality form. The way it's written now says 6 is greater than or equal to x, which is greater than or equal to 2, which is true. However, we always want to write it from the smallest number to the biggest number, or from left to right. So we just flip everything around and say 2 is less than or equal to x is less than or equal to 6.